This is the last of the four-part series. So we are drawing to a close, but today's topic will be iceberg. So we will scratch the tip of the iceberg for two reasons. One is not to be boring. B, relative to the other topics, I think this is a little more theoretical and more of sort of the internals of table formats as opposed to something more practical. Yet it is something important to know about. The third, yes, the third reason is I have to leave. So, so in that order, again, thanks everybody for having been through these sessions. I hope it was of some use and learning. If anybody is not on Wi-Fi, now is a good time to get on the Wi-Fi. We have limited bandwidth. Please don't download torrents or Bitcoin mining, anything. Okay, it's customary to do a recap, but we will keep this brief. How many of you were through the last 3 sessions? Okay, at least when you are the most dedicated of the Lord. Okay, how many were through the last 2 sessions? Okay, some more, all right. How many just the last session? Okay, so some of you have been through Spark. The vast majority, however, has not been through Flink and Kafka. But so let's just recap again. It's I mean, this session can also be interactive. We don't need to go through all the slides, but we started this series with one goal in mind. What is that goal? How do you build sub-second, quote-unquote, real-time data architectures? That is, something happens in your business. How do you crunch an insight out of it in 0 to 1 second? And what kind of data infrastructure is required in order to do that? There is an obvious AI angle to it. The AI angle is you need to be acting upon, for reasoning purposes or for retrieval purposes, you need to be acting on the latest, greatest data, not data that was stale 10 minutes ago. So data freshness is an important aspect. So that's been the key theme behind the real-time data masterclass series. So the first session was Kafka. What the heck is Kafka? Distributed sharded commit log. You have a stream of events, you send it to a big streaming fire hose like Kafka. So that's what it is. It's a distributed sharded commit log. It's an event journal. Whatever happens, write it down first, then act upon it later. Reliable data exchange pipe. So reliable is make sure you don't lose the data. So reliability comes as a result of that. Fan out means write the data once, read it many times. Big ecosystem. The ecosystem is that of connectors. How do you get, I mean, nobody expects Kafka to become the database. So often data is actually coming out of your databases, SaaS applications. These are the systems of record where things happen. But the fact that something happened is picked up from these systems and journaled into Kafka. Also relevant for stream processing. What is stream processing? Processing events in flight as they come, as opposed to, I will do it every night. Right? So that's the recap. We also did a session on Flink. So Flink is stream processing first class. So what is second class? Second class is what we did with Spark later on, right? So Spark is mainly batch processing first. Flink is stream processing is primary. Batch is a subset of stream processing. A table is a snapshot of a stream at some point in time. In fact, today's session will actually dive directly into tables. So how does Flink work? You write a data stream API program, how to read records from Kafka, how to do time windowed aggregations, how to manage local state, and then basically how to emit some transformed data back into Kafka or some other system. And the API for doing that is offered by Flink, and the entire program runs on number of nodes, right? So it's run in parallel, and that's what the job manager does. Okay, so we went through a little bit of data stream API, table API, Flink SQL. There are other things that you can do with Flink. Namely, you can do complex event processing, You can even do machine learning, right? And you can do state-driven functions, lots of different things. So again, something to be aware of, which we will also touch in this session, is what is batch processing, what is stream processing. Okay, batch processing is very simple to understand. Get a big bunch of data, transform it all at once, put it somewhere. Stream processing is the same thing, but not truly acting upon micro batches of data, but on every single record as it arrives in the pipe, one at a time, perform time windowed operations, and it's relevant for all these use cases. So if you ever use Datadog, if you ever use Uber, you are absolutely using something that has stream processing technologies underneath. So observability, fraud detection, IoT, or even if you go buy something on Myntra, that will be a lot of stream processing behind the scenes. Again, what's relevant? Stream processing is read, process, write loops. Why is that important, and why do we keep coming back to that idea? Because we need what is known as atomicity. I did this, I took this data, I acted upon it, I put this through this transform or through this functional operator, and then this was the output. So that allows us to make reasonable assumptions about what happened inside the pipeline. So essentially, stream processing is all of that, but with a number of other distributed processing primitives built into it, which is operators, bring your own custom processing functions, also known as UDFs, manage state under the hood, tasks fail, computers burn down, so therefore recovery. Most importantly, in stream processing terms, handle late arriving data, okay, and be a big fault tolerant buffer, which is kind of what Kafka is. It is a shock absorber between systems. Okay, so this is kind of what stream processing does. Essentially, we are in the world of processing massive amounts of data in parallel so that you can do something in 0 to 1 second. Okay, so that sets the stage for today, right? We're going to dive into Apache Iceberg.
Are we covering version 3 today for Iceberg?
It's a gentle introduction to Iceberg, but we will cover the latest, greatest. I mean, depending on your interest, we can do some Q&A as well.
Yeah, recently they launched V3, right?
That's right, they did.
How does this connect to whatever we went through, like brain?
But you will be stealing my thunder. The rest of the 10 slides is to talk through exactly that. Yeah, I mean, it does.
Some reason to pick this, right?
Absolutely. I mean, so the reason we have picked 4 technologies here, Kafka, Spark, Flink, that's the sort of trifecta of how do you run stream processing workloads. You need a big data buffer in between. That's the shock absorber that I spoke about. That's Kafka. But in order to process it, you need a different set of technologies, right? That's kind of where Spark and Flink fits in. But you also need, a strong table format, just like what is a database table, but you need the definition of a table format, and we will dive deep into what table formats are, file formats are today. But you need essentially the data that you process, where does it go? It lands up in a table somewhere, right? So that's sort of the very high level view of why you need a table. And once you know why you need a table, which is easy and obvious, you know why you need an open format for it. Okay, so we'll come to it.
Is this got something to do with vector data?
It does not necessarily have anything to do with vector databases, but
There is a perfect concept, I think you're covering that. So there's a puffin file which actually they use for the indexing purpose. There is a vector concept. I think I don't know whether you'll be covering or not.
yeah, I mean, our emphasis today is on Iceberg. It's not about vector.
But I think there is nothing called vector and all. It's a typical, it's more like the actual file format, just we have metadata and all.
Okay, so let's start off very briefly. Again, it's good to do a historical recap, right? So pretty much every data processing technology that we have derives from a lot of computer science theory that has been extant since the 80s, the 90s, and most remarkably augmented by what came out of Google, MapReduce, in 2006. So it was the dawn of the big data era, right? So big data then was data that did not fit into a very big spreadsheet. I'm joking. Okay, it did not fit into a large database. It did not fit into one machine. So anything could be considered big data at this point in time, but consider that was largely many hundred gigabytes, maybe up to terabytes of data. Today's scale, everybody generates petabytes of data, and the powers often go up to like 10 to the power of 23, so like zettabytes of data. It's huge amounts of data. So basically, data infrastructure to process this data has evolved because of different reasons, right? And usually one factor there is scale. So today what we'll talk about, I know I haven't introduced you to what a table format is, but it's useful to survey, the keywords here, right? We started off with Hadoop, and once people had lots of data in Hadoop, you needed to figure out how to find the data. Where the heck is the data, right? And that's kind of where data that describes the data, which is metadata, comes in. Hive was a metastore, primarily built for Hadoop.
Still there.
Absolutely, still there. I mean, no, I mean, we still have COBOL, we still have Cold Fusion, we still have Solaris machines. We have everything, but of course, it's a little bit of what's current. But absolutely, as you said, there is still a strong Hive angle even to Iceberg, which we will talk about. So we can say that all of these broadly map to first generation formats. So I have output data. Where does it go? It goes into files. And how do I query something out of a file? It's usually through establishing a table metaphor, right? You might also recall last time we did this, I think we spoke briefly about row-based formats and columnar formats. Again, we'll revisit it. But let's finish the survey of keywords. First generation, we had these things. Parquet is what is the columnar file storage format that came out around 2013, was donated to the Apache Foundation. And then in recent times, in the last 7-8 years, there has been a big explosion of how do I have one table that can be read by multiple analytical databases, query engines, etc. So we will, while today's session focuses only on Iceberg, we will briefly talk through Hoodie, we will talk through Delta Lake, we will talk through lots of other things that are also emerging, such as Apache Stable, Delta Uniform, so on and so forth. Okay, so the essential theory one needs to know is understanding that storing data is not for the sake of storing data, right? It's never for just purely backup and archival purposes. So if it's purely for backup and archival purposes, we don't need to store metadata, we don't need to index it, we don't worry about querying. We'll figure out how to read the data from top to bottom and find what we want. Somewhat like how my downloads folder is organized. But in order to query data, you need the data to be laid out in a useful way rather than querying something out of a dump. So there are really how do you store data on a drive is basically a key aspect of how people build system software, how computers are built, right? So most transactional databases, you have Postgres, MySQL, Oracle, any transactional database. You're usually interested in storing a row of data together because a row of data is what you act upon. Let's suppose I want to store a customer. I'm interested in all of the customer's attributes, all fields, all at once. So I'm never interested just in the customer ID, right? I mean, that's the primary key, but usually I want to retrieve the whole customer object, let's say, right? So therefore, row-based databases store all the data in the row contiguously. Why is that so important? Because the way one reads these things out of the disk is, you ask the Linux kernel, okay, go read the data for me in this sector on my disk. So the operating system cannot do point reads, right? Usually it also has to seek to an offset, right? Go to this point If it is a spinning drive, such as a hard drive, it's even more expensive. With SSDs, it's easier. But in general, what do you need to know? It's very wasteful to retrieve, only 10 bytes of data. So usually, the way operating systems behave is that they are very well tuned. Not just operating systems, even hardware is very well tuned for around 4 kilobytes of aligned reads and writes. So therefore, you have to retrieve a lot of data at once. We don't usually see it, but that's very important. So in row-based databases, rows are stored contiguously, but that sucks for analytical data. For analytical data, you are more interested in asking a question: what is somebody's lifetime value? So you don't need to actually load up all the data about each customer. You're only interested in how much sales have they done, and you want to retrieve that and aggregate it together. There are a class of databases known as hybrid transactional analytical databases, also known as HTAP, which claim to do both. Okay, but that is not without trade-offs, right? So a HTAP, yeah, SAP HANA is a HTAP. Okay, but PIDB is also a HTAP. HANA is a good example of a HTAP. But basically, this is my personal opinion. HTAPs suck, right? They are not without trade-offs, right? So it's like it's a little bit like this. I mean, we see this even amongst humans. There are people who are good multitaskers. There are people who are good single taskers. So who's more efficient? It depends, right? So fundamentally, everything in computing is about trade-offs. So whenever you say I will do two things well, you will usually end up doing both the things badly as opposed to doing one thing well. So, but with that being said, some databases do live up. In recent times, you have the concept of multimodal databases. One database that also allows for graph, or NoSQL, SQL, everything all at once. So it's an emerging trend, but there are only about 100 to 120 databases in the entire world, right? At least the most popular ones. So the database industry is well understood. There is scope only for a few things. So either you have to do something really novel, but most often in databases, it is about doing one thing really well, where you are better than the others. That's what makes people buy your database. So in general, most can be sorted into these two categories. So that brings us to the point. If you want to store analytical data today, you have a CSV. CSV is a row-based format. How do you store analytical data for fast retrieval and for doing aggregations, so on and so forth? You store them using a column-based layout. Okay. So every data lake that is built today will usually be built on top of Apache ORC or Parquet as a format. For the curious nerds amongst you, it's good to understand what a file format is or what a file layout is, right? So I will not go into all the details. That's beyond the scope of this discussion. Certainly beyond the scope of 6:30 today. But in general, it's organized like this. Every such file will have a magic byte to begin with, which says what kind of a file is it. In this case, it's a Parquet file. So Parquet stores all these columns in row groups. Okay, so groups of rows together, and there will be lots of metadata, which is what's the page header, and there will be some aggregated stats, repetition levels, definition events, values, so on and so forth. All of this is kind of what is stored in each Parquet file. So Parquet is the gold standard of how to store data in a columnar format. Every Lakehouse usually does this, right? So basically CSVs will be terrible for storing analytical data. You need something like Parquet. Okay. So Parquet has been around for quite some time, but having a file format is not good enough, right? So you also need to kind of be able to treat your data lake. By now, I'm guessing everybody has a vague idea of what a data lake is? If nobody does, I'm happy to go into some detail there. Okay, all good. So, I mean, what's a data lake? I mean, basically, it's the idea that I have a ton of data in my enterprise. I have some people are running applications. There is observability, telemetry data. Then there is business data, operations data from, let's say, ERP, CRM systems, blah 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 blah. And I have an analytics team, whose job is to crunch insights out of it. So what do I do with the data? Bring it all into one place and write them as Parquet files. And that's broadly what a lakehouse is. It's a data lake or a data warehouse. Both are very related concepts. And in recent times, everybody uses the Databricks terminology. It's not a lake, it's not a warehouse. Is it a plane? Is it Superman? It's both, right? It's a lakehouse. It is a combination.
Lakehouse is actually a word which is a combination of data lake plus warehouse.
That's right.
So that's how it's taking the hand.
Absolutely. So, ClickHouse is also similar. ClickHouse is also an analytical database. No, it has a completely different, its own file format. So every database has its own file format. Okay, they all optimize for what's important for them from their internal interface perspective. But in general, Parquet files are laid out for a big engine like Spark or Flink or Trino to come and basically process the file. So that's kind of what it is there for. It only describes the file format. So it's similar to just Avro, what we spoke about. So how do you usually send data to Kafka? Is you serialize it as Avro. So Avro is row based. So in many ways, the Parquet is the columnar version of Avro. But different databases have different internal storage formats, let's say. No, Lakehouse has mostly append only data. You almost never do inserts, upserts, semantics. Even if there are upsert semantics, it's usually based out of an LSM tree, and therefore it's mostly eventually consistent. It's not for transactional data. Yes, transactional databases need to perform at very, very low latency, right? Which is.
So I want to clarify. In Lakehouse, for example, Iceberg, you can do insert update all operations you can do.
Yes, you can. But not in the same way. It's still in an analytical context.
If you're doing in a sequential manner, right, one row of your updating, it's very heavy, it's very costly operation.
It's very expensive, and the data that you are acting upon is columnar in nature, is not rows. So, but fundamentally, analytics and transactional databases are completely different beasts, right? So basically, let's assume you have now 10,000 Parquet files. So how the heck do you find, the data that you want? You want to find customer orders data. Where do you go find it? Right? So in the old Hadoop world, where did that metadata come from? It usually came from Hive. But in any case, you want to be able to query the data in your lakehouse. Otherwise, it's useless, right? And if you need to query the data, you need to be able to define what a table is, okay? And where the underlying data that defines the tables, where does that data sit? You need to be able to describe this so that engines, which could be Spark, Flink, anything, they know how and where exactly to go find the raw data files, which is essentially Parquet files under the hood. So therefore, you need to define what a table format is, okay? So what has also happened in the analytics world is people have come out with query engines. Query engine it's a generic engine which you can reuse. Okay, it understands SQL. When you express that you want customer orders, it knows, okay, I need to go perform this aggregation, I need to go find this data, and I need to go do X, Y, Z. So usually these can also run in parallel. They can do a lot of things. In many ways, they are very similar to processing engines. just like Spark and Flink. So processing and querying kind of go hand in hand. But for all these systems, they need to know where the data is and what layout is the data laid out in, right? And therefore, you need a table format to express that. Okay. So second reason is you need multimodal processing. What is multimodal processing? Sometimes you might want to do just big batch processing. Other times you might want to read the latest, greatest data at, I don't know, micro batch intervals of 30 seconds or data as it comes in, just through stream processing, and then process the data, right? Many times you might also want to do time travel. So what is time travel? It is data as of yesterday, right? I want to act only upon those files. So that's there. You might want to do audits. Often the schema, today you have a user field, it has an email and username. Tomorrow you decide to split that. Okay, not name but first name, last name, middle name, or you insert a user address field. So in all of these cases, basically the way the underlying file is laid out needs schema evolution. Okay, so all of these things are best described through an abstraction, which is kind of what a table format is. So for those of you who are practitioners, you'll see that it actually sits in this hierarchy. I don't know if you can really clearly read, but at the bottom is your storage layer. That storage layer is typically what is the cheapest SKU in the cloud, which is S3, Azure Blob Storage. On top of that, you write files for analytical purposes in a file format. What is that? It will be Parquet, Avro, RC, JSON, CSV if you want to be terrible at it, etc. Over and above this is kind of the layer that we're talking about today, which is the table format. Okay, so today we're talking about Iceberg, but Iceberg is not the only table format. That is why you need to go and recap what we spoke about, right? As there are multiple table formats. For example, Databricks, which is the biggest company in this ecosystem, their proprietary table format, which has been open sourced in recent times, is Delta, right? So the lake built on top of Delta, the protocol and the format is Delta Lake. So there's also Apache Hudi. Apache Hudi is basically came out of very large scale Hadoop clusters in Uber, right? And that has a separate company backing it. It's called OneHouse. Then there is Iceberg. Where did Iceberg come out of? We'll see. But over and above open table formats, you have a layer above. What is that? That is, basically what a catalog is. Okay. So multiple tables. It's like multiple databases, multiple schemas aggregated together into one place. Okay, somebody is doing a walkathon. Okay, I don't know what they're protesting about. I hope they're not protesting about Iceberg. Okay, all right. Okay, so what's a data catalog? Catalog is basically figuring out where the tables are. The table describes what Parquet files are where. A catalog describes, what are the tables that you have, right? And over and above this, who uses all of these? Query engines. So there are many engines which can figure out, how to go find the right files and how to aggregate so that when you speak SQL, they can return answers. So Spark, Flink, etc. They all fit in the processing engine, query engine spectrum, and that's kind of what your data ecosystem looks like. Sorry. Where do you use traditional BI in a Lakehouse?
No, he's saying what is the use case where we don't have to use Lakehouse directly with the database? That is this question.
You want to bypass the Lakehouse and directly do BI.
Lakehouse is good, but there are a lot of places where you will still use traditional data warehouse. It's not necessarily with
Right, right. Yeah, I think there is still a good case for BI without all this Lakehouse complexity.
Give you a use case. Let's say if you are not doing any operand operations, right? If your data is keep on appending, you are doing some append. In that case, probably you can go with the data.
No, I mean, I'll give a more qualified answer. I mean, that's one part correct. I think if you don't have large scale data, I mean, for example, you're not using data for machine learning at all. Some of the data that you do, it has no useful consequence outside of somebody's dashboard for reporting purposes only. Then you don't need a lakehouse. Then pure BI on top of warehouse is good enough. But if you have a use case for multimodal data processing, I need to do with some real-time data, I need to do some batch data, I have some data scientists who want to train models on it, I want to take some of the data, aggregate it and send it back to a transactional databases. If you have any of these use cases, then you need a lakehouse. Otherwise, just BI over traditional data warehouse is good enough. Does that answer your question? Okay. All right. So that finally brings us to what we are talking about today. So there are multiple table formats. Had a question? No. Okay. Okay. There are multiple table formats. You should remember. We will talk briefly through Hoodie. We'll talk through Delta. We'll mostly do comparisons. Okay. But where did Iceberg come from? Iceberg is in some capacity, it's addressing the limitations of Hive. Okay, just like other Apache Foundation projects, Iceberg came out of some guy's pain. Okay, that guy, sorry, I don't remember his name, was in Netflix, right? And Netflix, it was terribly hard to find data. Therefore, they had to invent a table format, establish metadata catalog, all that, right? So it is the most widely accepted table format as of today. Very large ecosystem. So kind of what Kafka is to a stream, Iceberg is to a table. Okay, so that's how you need to look at it. And it's widely supported. If any of you have observed in recent times, the people behind this, they went on to found a company called Tabular, and Tabular then got acquired recently by Databricks. So it's been through quite a bit. In general, what happens with these ecosystems is, one large company takes something, makes an open standard out of it, and then the ecosystem builds up. Why? Because people should not have to come up with new tooling, new format definitions, etc. So it's a little bit of the game of the big boys. So Iceberg comes out of that. But what does Iceberg really look like? Is Iceberg has a catalog. The catalog is kind of the system of record of tables. It's what's the next layer above. But Iceberg itself provides these capabilities, right? Which is be a way in which you can find data, do multimodal processing, time travel, schema evolution, along with a commit and transactional protocol, right? What exactly is it physically is the next question that comes about. So usually in the analytics world, mostly everything is done on top of large blob stores, object stores like S3. So files once written are immutable. Okay, so that forms the basis of every transactional commit protocol. Once the file is done, it's frozen. It's never gone back and updated. So again, in this case, the protocol here works mainly through a metadata layer, which has a bunch of manifests, which describe what was a file at a point in time. Basically, it strongly follows the Unix philosophy. Everything is a file. So in other words, it's describing locations and the layout of a number of different Parquet files, which are related in the sense that it is part of one logical table. Okay.
So I have a question. Can you go back to the previous slide? So I have a file. I actually done 50 operations, right? To a table called ABC. So I will have 50 metadata files, right?
Possibly, yes.
As a metadata file, it will be a pain actually, right? This guy will be able to, he has to scan through all the metadata file and right?
We'll come to that. I mean, usually one aspect of findability is not scan everything and not read everything. So usually these, I mean, the one is, essence of the table format is to say how do you find things. Second aspect is how do I prevent you from having to scan and read everything. So there is an element of indexes, findability. We'll go through that. And again, a number of your questions in this today's session might actually be covered practically through Avinash's demo. In terms of looking at the physical file layout, it will make more sense.
I have questions on compaction.
On compaction.
Questions on the latency part. We'll cover. Okay.
For sure, for sure. Okay, so to answer your question, right? I mean, the whole essence of a table format is store enough metadata to avoid scanning everything. So if I have to find something, if I have 10,000 files, going through every file would take, computationally it would take, so much amount of time that it basically stops making sense. So usually what is a good table format is something that describes the underlying Parquet files with enough metadata such that you know exactly the data that you intend to find. Let's say I intend to find, I don't know, people in lexicographical order, people whose names begin with A and B. So therefore, I shouldn't have to open all 10,000 files, right? I should basically know which Parquet files contain customers whose names start with A or B. So that's kind of where indexes and metadata actually comes into play. So the essence of the table format is store enough metadata to avoid scanning everything and reading too many Parquet files. Secondly, if there is a little bit of a bimodality here, just keep this in mind. We don't need to go into details. If it doesn't make sense, it's okay. One of the problems with building databases is there are only two problems, right? How do you build a good storage format? Okay. And the second thing is how do you build a good query planner? Okay. So it's like, do I store my stuff well so it makes it intuitive to query it? Or do I better develop a better query planning algorithm so that even if the stuff is in pieces, I can kind of go piece it all together. So those are the two problems in building. So again, even in the case of Iceberg, basically it allows query engines to do efficient planning such that planning can be very efficient for large tables, okay, to make sure that execution is smoother. But all analytical databases, all lakehouses are prone to small files. So if you have a shit ton of, sorry for my French, crap ton of small files, then it is basically going to be slow. In that case, being able to do large scale vectorized execution, compaction, etc. is kind of what it reduces to. But the good news about Iceberg is that it has the widest amount of adoption. So take Presto. Presto is a query engine that came out of Facebook, or Trino.
Presto is now it's changed to Trino. It's now
Sure, absolutely. So Presto, Trino, all of these things are really good at working with table formats. That's the essence, right? So
Multimodal, right? Now for multimodal AI data sets, how efficient is Parquet and when does it actually make up?
Parquet is quite efficient. It does not really have any unnecessary overheads. But with that being said, are there better columnar? Yes. So usually Parquet is not where the problem is. Reading a single file and basically mapping it to memory, and as long as you know the schema, is not very difficult. But even there, it's like XML versus JSON, right? JSON is much more compact, XML is much more verbose. So even with Parquet, there are better alternatives that are emerging. For example, in recent times, there is a format called Lance. Lance is, in many benchmarks, it's orders of magnitude faster than Parquet. But then again, the adoption for Lance is kind of very, very poor, very early.
Actually, Lance is still evolving. I don't think it is people are still
There are users.
Enterprise level companies are no problem. Any one of you using the platform right chat? I don't think so.
I mean, I agree with you. So it's early days, but the thing about is, if format is much more compact and it's so much more efficient, it will eventually find usage. But you still need a table format to describe where your lance files are sitting, right? So ultimately, the quest for data, metadata, catalogs, this hierarchy to describe where is the data, two query engines, which know how to do lots of these things in parallel, is kind of the essence of our use case today. I mean, it's been largely popularized by Delta as a good commit protocol. How do you do liquid clustering? I mean, often when you're actually writing this data, you don't upfront know what is the best way to write the data. Okay, so there is an element of how do you do automatic partitioning, avoiding partitions, lots of different things. But in any case, we are talking today about the read side. Sorry, sir, go ahead.
Can we do here, let's say while planning, like workflow or pipeline, and make it an entity and keep it, and whenever I start, I can run the execution. Is it possible?
I'm quite.
Let's say planning, right? Once you keep it, see, when you are doing leading the query, it's like load out queries, like, see, sometimes we do upstream to downstream data flow happens, right? Similarly, see, this is, I'm finding, let's say, hookup, then metadata, then manifestation, things like that we are doing, and read the data file. This, see, normally pipeline what happens is you can get the one place or one format or another pattern. So similarly, is it, I'm just trying to correlate it. Just like pipeline we will do in Kafka and other tools, right? That kind of things is possible or not?
We can do pipelines here. I mean, as long as you describe a table is an input, a table is an output. So what happens behind the scenes is the table is just describing where your data files are. That's kind of what it is doing. It doesn't play a role. The actual querying, pipelining part is in your query engine. Okay, this is about a protocol for how files are laid out and how metadata is described. Think about it as Delta Lake, but a more open source, open standard variant. Okay, so practical example. So if you just say select star from some schema table, what actually does your query engine? What will Trino do, or what will Spark do? Right? It's going to first query the catalog, which can be in this case Hive, Nessie, anything else. Okay, and then read the present metadata file. So there is a single atomic pointer at the top of every iceberg table. It says, okay, this is the current snapshot. So again, we'll come back and address what snapshot isolation is. And then it's going to actually read the manifest of files. What are the Parkway files?
Files can be more than that also.
Yeah.
Can have more than one.
Yeah, absolutely. I mean, the atomic snapshot points to a certain version of the files. That itself can describe more than one file. Okay. Read the manifest list, okay, of what files are actually involved. And this is kind of where a lot of smart planning happens. So for example, if you know statistics about some files, what's the starting point, what's the ending point based on column stats, etc. So you can actually do partition pruning, where not to go find the data that you're looking for. So it is largely like a library index, right? And at that point, you finally found out which files match, okay, and therefore, what parts of those files do you need to read, which is usually what columns, and that's kind of how query engines figured out through the catalog and through the table what files do they need to go process. Okay, so that's more about the read path. So you issued a SQL query. How did it get planned? How did it come about, etc. Now, how does all of this get written, right? I mean, many times with the Delta protocol, etc. If somebody is using Databricks, we largely don't care about, how the underlying protocol works. But again, I think this will take too long to go through, but the important aspect is the read path is often very easy with all kinds of databases. The write path, on the other hand, is much more difficult and much more nuanced. Why? Because you're going to deal with concurrency, right? You're going to have multiple writers trying to write at the same time. So in that worldview of computing, you need to think about locks, semaphores, mutexes, or concurrent versions, which is kind of what MVCC is. Or how do you do optimistic concurrency? Okay, I'm going to try and write the file. I will try it, but if there is a lock, then I will throw an exception. Or pessimistic concurrency. In this case, Iceberg is tuned for MVCC. Optimistic concurrency, it will try to write. If there is another concurrent writer, then it's going to tell you, sorry, I can't do that. It's locked. But fundamentally, the other principles are it's immutable metadata, which is a common thread. Most importantly, whenever you're doing a write, if somebody had started reading that table already at that point in time, so that becomes a race, right? So for example, you have just updated some data, another thread attempted to read what's in the user table. So if they coincide down to the same, let's say, millisecond, microsecond, should they see the data or should they not see the data? So that becomes like a speed of light type issue. Oi, enra? ಕೆಳಗಡೆ ಹೋಗ್ಬಿಡು. Okay, so that becomes a little bit of the sort of speed of light type thing, which happened first logically, and finally concurrency is if you take time as a continuous unit, not something that's discrete, you can always go down to nanoseconds, picoseconds, which came first, but that's not how it works, right? So usually whenever you're doing a read, most databases apply the principle of snapshot isolation. When your thread started, it's going to basically work on a snapshot of the data when the thread actually started, as opposed to what's going on right now. That means data that you do during this query is actually consistent and kind of repeatable, as opposed to the data changing constantly. So
Patterns, whether we do concurrency and partition. Two-phase commit is there and different patterns are there. What kind of different patterns is following only one or can we have multiple patterns?
you don't follow the pattern here because those internals are handled by Iceberg. The Iceberg is the specification and the protocol. So anybody who's doing an Iceberg writer will use Iceberg libraries, and they will essentially end up doing this.
Any idea what they follow?
It will be a 2PC. So to do that, there is
parameters like how much you should read. I think there are some parameters. I don't remember.
all of those are tunable. Fundamentally, it's about this. You take a lease on some file saying only I can do this at some point in time. If there are two, how do you do them? Basically, you have to figure out which writer has a higher epoch, who started later, who is not dead yet, how do you kind of fence zombies. So there are well-known patterns in kind of building distributed systems, and how do you handle threads, and how do you handle concurrency. The two approaches here are MVCC, which means you can have multiple concurrent versions. So, and those can essentially be very lock-free. Or whenever you need to actually update something, and if you need a single writer scenario, you use optimistic concurrency. You can do pessimistic concurrency, but it's with a very large cost of blocking people off. Unfortunately, I can zoom in, but if it's not very readable, there's not a lot I can do to help. That's because this projector sucks. Avinash, is there any way we can zoom the thing here? How do I zoom in? It's better? I can read it out if it. So basically, the write path involves read the current state, right? And basically scan which files need to be written, write the data files, determine the actual base metadata, see if there is a conflict. is there a concurrent writer scenario? If yes, abort. Otherwise, if it passes, write the metadata file. So that means, one write can be rejected, but basically it will have all or nothing semantics. So you will never have the metadata and the files out of sync. So they will always happen together, or they will all fail together. So that's kind of the basic definition of the transactional protocol. It has ACID semantics. Okay, and of course, finally, when there is a new version of the file, you swap out atomically a pointer at the top pointing to the newest. I'm sorry? Multi-version concurrency controls. Okay, an essential aspect of systems that generate changes, analytical data, is time travel. So, not the physics side of it, but this time travel here is read from this some table as of some date, right? And how does that happen? It's basically because of the time epoch being managed almost as an internal partitioning primitive. So it's kind of stored, it's out there in the metadata, it's out there in how the file formats are laid out, and basically how the table definition actually points to multiple versions of the files. So
I have a question here. Maybe it's too early to ask. So here, so there are five times, right? Is it T1, T2, T3, T4?
correct.
I will have 5 metadata files.
That's right.
Let's say I'm at this point of time, there is a automatic compaction happening. So it's trying to merge all the files in a single metadata file. At the same time, I'm trying to do a write operation. What will happen?
You're trying to do a write operation or a read operation?
Right.
If you're trying to do a write, it will have a lock. So only a single writer can take a lock.
Action is happening, right?
Huh.
And then trying to write.
Yeah.
It will wait for the
Yeah, of course.
action complete.
Yeah, absolutely.
And,
So the compaction process, if it's actually modifying the commit files and swapping the pointer out, it is a blocking operation. Other things will have to wait for that to happen.
and what about the read? What will happen to the read?
So when you do reads, you have a snapshot isolate. So
It will have a stale version, right? If I do
anything is stale by that definition, and that's why snapshot isolation is very important, because the thing that you're reading midway through your call through a transaction, data cannot change, because that leads to what people call as spooky action at distance, where you're unable to explain why that happened. So snapshot isolation means that the database gave you a consistent snapshot of what's been written and committed at that point in time. That's what the readers read. But while you're reading it, the data might change. But that does not mean you start reading new data at that point in time. So until you finish the read, you are reading a snapshot. That's a very essential aspect of how databases maintain reasonability.
let's say I'm doing compaction here, right? How many files will appear when I see and go and get the S3 bucket? How many files will appear? Because I think all will get compacted, right? So
Correct.
how it will play?
We can look at it practically, but basically it depends on how aggressively compaction runs, what it attempts to do. What is compaction doing? You want to take smaller files, aggregate them into bigger files so that you have fewer files to read. Essentially that, right? So obviously the number of files here will reduce, but it depends on what level of compaction, aggressive, conservative, how much history do you want to conserve, all of these factors.
There are a few ops to the compaction job that we do. So that depends on the case. If we enjoy it well.
Yeah, we have them.
Who decides this number of files? How many files?
It's configurable, but usually the engine that's managing these files has to sit and do compaction. So you decide. Ultimately, if you're writing a query engine or a processing engine, you decide. If a vendor is writing that for you, they decide. And they might offer configuration options to you as well.
Cost of
I mean, it is such an essential part of database theory that it's not like you pay an extra cost. It is a bare essential, because otherwise you're reading something now and 2 minutes later something else is written there. So that cannot happen. So there is no cost. Is there a finite cost to it computing wise? Yes, but it is such an intrinsic part of building a database that you can't look at it as an extra cost. You have to look at it as an essential cost. So I will have to maybe take a pause here. Avinash, is this better explained with a practical demonstration, or do you, yeah? So I'm going to take a pause, but let me just leave you with a sort of preview of what is to come. We are also just at time. Whenever you're working with lots of different files, etc. Again, we mentioned computer science is fundamentally about trade-offs, right? So two patterns emerge, right? So those two patterns are, how and when do you spawn new files, and when do you merge files, etc. These things have a big implication on what you are intending to do, whether you're intending to do stream processing or whether you're intending to do batch processing, so on and so forth. So those two patterns, again, we'll not go into the details, maybe we can have a conversation, those two patterns are called copy on write and merge on read. So remember these two keywords. So the way you tackle these problems, Apache Hudi as a format basically gives you both these options. When you do a table, you can choose whether it's a copy on write table or a merge on read table. For those who are the curious folks amongst you, I would highly recommend reading Alex Petrov's sort of building databases, designing data intensive applications book. It's really good. You'll cover all of these things largely in a Cassandra context. But be aware of two things. Ultimately, all databases store data where? In a binary format on files. So the two patterns and files cannot grow infinitely long, because then they'll become difficult to manage. They also cannot be very small, because then it becomes opening new files, new handles, and it becomes just the overheads of file management, bookkeeping itself becomes too much. So therefore, you have to operate within certain constraints, and in all of those cases, it will have implications on speed of processing, throughput, latency, how long does it take to do what. So those trade-offs are reflected in these two patterns: copy on write, merge on read. In Iceberg's case, Iceberg doesn't necessarily expose it to you, definitely not at a table level, but at the level of each query transaction processing each file at a given point in time, or a bunch of files at any point in time. Query engines such as Trino, Spark, etc. can selectively choose to apply COR or merge on read patterns. Okay, and that is very useful. So just as a sneak preview, I can tell you, for example, for stream processing, if you want to process lots of data landing into these files at the lowest possible latency, you will need MOR. If you're doing lots of batch processing, you will most likely prefer copy on write.
The same thing. Why is Spark engine is fine? You can get the data from the data lake or from storage.
How?
Why was having that? Why can't the Iceberg do that?
Iceberg is the table format. Iceberg it does not have any computing attached to it. It is just saying how files must be written, how does a protocol happen. It is just the storage layer. It does not have any compute. It's not a database. It is a definition of how database-like engines can act upon some data.
So computing happens in Spark.
Absolutely.
It's not readable. Slide from
Yes, I think we'll send those slides across, but Avinash, maybe you can see what you can do. It's white background. But we'll break shortly. But here are the three things that I think we can very broadly talk about. Okay, if you use Iceberg, what do you have to gain? I mean, today's session is about iceberg. So the main important things that you'll gain out of it is, query engines such as, Spark, Flink, Trino, DuckDB, very popular in recent times. I know. ಏನಾದ್ರು ಮಾಡ್ಬೋದು ಅದನ್ನ. Or let me change the background. Is this better? No. God. No, yeah, don't stop it.
Change the focus is on.
Okay. This is better? Okay, this is better. Okay. All right. Okay, so yeah, we'll break shortly. Okay. Iceberg, Delta, Hoodie. Okay, there are other things outside of this. Iceberg, main gains. Okay, most widely accepted table format around. Okay, so lots of engine portability. All engines work. They just work with Iceberg. Okay, so you don't have to care. Partitioning, etc., is an internal detail. Partition evolution, schema evolution is all supported. S3 tables, native S3 tables in recent times. AWS introduced S3 tables, so those are native Iceberg tables. Strong snapshot isolation for batch, what we spoke about. Okay, but there are some trade-offs. What are the trade-offs? If you want to do lots of upserts, it's less efficient than Hoodie. Hoodie, we mentioned, comes out of Uber. So compaction tuning is kind of still the operator where query engines do that, usually not exposed outside. So which catalog do you choose is also another decision. So if you want to do large scale stream processing, can you do it with Iceberg? Yeah, Netflix does it. But does it suck? Yes, to some extent. Okay, somebody said it. Okay. I mean, I'm doing a session about Iceberg. I can't shit on Iceberg in this. Okay. Next, Delta Lake. Delta has been open sourced. It's no longer a proprietary format. Probably it's best in class for Spark integration. Why? It's Databricks' baby, right? Liquid clustering means you don't have to decide how files are partitioned. Lots of governance, Unity catalog, all the goodness. It just works. Databricks ecosystem is essentially the world of notebooks, so it works. Trade-offs, you become a Databricks customer most often. Okay, so there is also Delta Uniform, but it's not. I have less to say about it. Hoodie, on the other hand, in my opinion, I'm wearing a One House T-shirt. I have nothing to do with them. I'm not marketing them, but I really personally like Hoodie, but it is somehow been an underachiever in this ecosystem. Really good for low latency streaming style queries. In fact, when we say Hoodie, there is also another format that we need to talk about, which is Flink specific. It's called Pymon. Avinash has done a talk on it at some point, again, outside of the scope of this, please see it. There's also something called Floss in recent times, FLUSS. Yeah, that's also very interesting, but outside the scope.
Evolving.
Still evolving, indeed. Okay, so trade-offs. It's a small community. It does not have Databricks $100 billion company backing it. It has a $50 million company called OneHouse backing it. Query engine support is decent, but not too good outside Spark and Flink. So complexity, you have to own a lot of the operations. So when will you choose something if you want a mature format? Today, I think your option is still where if you don't want to be tied in into Databricks, the best format today still is Iceberg. Okay. Now, where does this coincide with streaming, Kafka topics, everything that we talked about? Most Kafka engines today or in near future, they will all be able to take a Kafka topic and automatically maintain its counterpart table, which will be an Iceberg table. So in Confluent, that proprietary technology is called TableFlow. Elsewhere, many of those things are also coming. In fact, in Apache Kafka, sooner or later, every topic will be materializable as an Iceberg table as well. So that's kind of where you're streaming data into Kafka, but the same topic can also be materialized as an Iceberg table. So that's kind of the unification of streaming and batch processing. So that's the actual summary. I think they're all.
Sorry, if you go back, right, I just want to give you some updates. Iceberg is on version 3 already.
Sure.
And I think they're going to release version 4 shortly.
Yes, this is outdated. Yes, but none of these things have necessarily changed.
Yeah, I think it's low slack, but I think this is a very evolving community.
Indeed.
Especially Iceberg, because many companies like Snowflake, there are a lot of committers, right? Also submitters. That's why it's evolving pretty fast.
Absolutely.
Iceberg.
So, yes, sir.
So I did some PVC with Iceberg previously and I have
Okay.
an application. So